Hello everyone, I'm Divyashree Maybe working as Assistant Professor in the Department of ECE, SJBIT. So in the previous video we have discussed about the generation of FM signal using a tank circuit, LC tank circuit, basically a Hartley oscillator, and then a feedback system like frequency locked loops. So in today's video we will be discussing about the demodulation of FM signal. In the last video itself I have given a brief introduction about the demodulation. So continuing with that, the FM demodulators, basically there are two types. One is the direct method and another one is the indirect method. Indirect method we have two types, one is frequency discriminator, another one is zero crossing detector. In indirect method we have a method called phase locked loop. So in general words I will just explain what happens in demodulation. FM demodulation, it is basically like a frequency to amplitude converter. So whatever the frequency variation is happening in FM wave, it will be taken as the input, and that frequency variation is converted into the amplitude variation at the output, so that you can get the original message signal. So what are the requirements of an FM detector is, it must convert the frequency variations into the amplitude variations. So whatever the conversion is happening, frequency to amplitude conversion, it must be linear and it must be efficient. So the demodulator circuit, it should be insensitive to any amplitude changes in the frequency modulated wave. It should only respond to the frequency changes. Even if it has any amplitude variations, it should not take that into account. So it should not be like too critical in its adjustment and its operation. So we will take up the first type of frequency demodulation, FM wave demodulation signal. We call that as a balanced frequency discriminator, or you can also call this as a balanced slope detector. As you can see in the block diagram, the input is FM wave, and the output is a message signal M of t. You have two such circuits. One is just a replica. One block is a slope circuit, another one is a envelope detector. So here what happens is, the frequency modulated signal in the slope circuit, it is applied to a tank circuit which is built in the slope circuit. So the center frequency, it is Fc, and the frequency deviation is delta F. When the frequency of the input increases, it becomes more close to the resonant frequency, which in turn increases the amplitude, or you can say output voltage. When the frequency of the input signal is decreasing, it moves away from the resonant frequency, which decreases the output voltage. So whatever the changes in the frequency we are sensing, now it is converted to the voltage. So frequency variations in the input signal about the carrier center frequency, it produces output voltage variations which is proportional to it. The output voltage, it is applied to the, next is the detectors with certain RC component, so that you will get back the original message signal back. So you can see here in the circuit diagram, it consists of two slope detectors. slope detector 1 and slope detector 2. And it has a center tap transformer here, that is at the secondary side. So whatever the input voltage is coming, it is having a 2 slope detectors, so which is approximately absolutely 180 degree out of phase. So there are 3 tuned circuits here. Out of them we have one is, that is the primary circuit, which is centered at the frequency Fc, and you have the above tank circuit here, which is tuned at the secondary of the T1, which is tuned at the frequency Fc, and it is having a variation plus or minus delta F. So its resonating frequency it is Fc plus delta F, and this one is Fc minus delta F, out of phase. So the lower tuned circuit of the secondary, it is tuned below Fc by delta F, so it is Fc minus delta F. And you have an envelope detector here, that is a diode and a RC component. So this R1, say let me take this as R1, C1, R2, C2. So R1, C1, R2, C2 are like the filters which are used to bypass the radio frequency ripples. So there are 2 output voltages, VO1 and VO2, which are basically the output voltages of the slope detector. So let us take this as the output voltage VO1, and let me take this as output voltage VO2 at this point. So the final output voltage, what is obtained, it is by the subtraction of these 2 output voltages. So VO, final output VO is equal to VO1 minus VO2. So the circuit operation depends on dividing the input frequency into 3 ranges. As you have seen, there are 3 tuned circuits. One is at the primary, 2 at the secondary. So suppose when Fn is equal to Fc, this is first case. When the input frequency is instantaneously equal to the carrier frequency Fc, then the induced voltage in the secondary winding T1, that is at this point, it is exactly equal to the voltage induced in the secondary winding T2. So the input voltage to both the diodes is the same. So the output voltage VO1 and VO2, they are equal but have opposite polarities. So what is the output voltage VO? They are equal but opposite polarities. So VO is equal to 0. This is the first case when Fn is equal to Fc. The second case is when Fc is less than Fn, less than Fc plus delta F. In this range of input frequency, the induced voltage in winding T1, it is higher than that what has been induced in T2. So the input voltage to D1, say this is D1 and this is D2. Therefore, the input voltage D1, it is greater than what you are applying on D2. Hence, the output voltage VO1 is greater than VO2. Therefore, the output voltage VO is positive. When this is greater than VO2, obviously this is positive output voltage. So what is VO? VO is equal to VO1. This is the second case. Coming to the third case, when Fc minus delta F, it is less than Fn, less than Fc. In this case, if input frequency within this range, the the induced output voltage in T2, it is greater than T1, means VO2 is greater than VO1. So, the negative output voltage VO2 is greater than VO1. So, the output voltage VO is a negative value. The negative output voltage increases as Fin becomes very much closer to Fc minus delta F. So, what is the output voltage? VO is equal to minus VO2. So, if you see this frequency response, we will understand there is a 3 dB difference, and this is a response when you are concentrating only on the upper tuned filters, that is here, and this is the response for a lower tuned filters. So, VO1 is greater here, and here VO1 is greater, here VO2 is greater, that is minus VO2. So, combining these two response, so we will get the response something like this here. This is with respect to the lower tuned filters, and this is with respect to the upper tuned filters. So, here if you see the responses, the circuit is more efficient compared to the simple slope detector. It is having a better linearity than the simple slope detector. So, these are the advantages. Coming to the disadvantages, even though linearity is good, but it is not so good enough to use it in very critical applications. This circuit, it is difficult to tune because there are 3 tuned frequency Fc, Fc plus delta F, Fc minus delta F. So, tuning in 3 frequencies is little difficult. And the last disadvantage is amplitude limiting is not provided here. These are the drawbacks of balanced frequency discriminator. Next is FM stereo multiplexing. FM stereo multiplexing, it is basically used for stereo transmission. It is a form of frequency division multiplexing which is designed to transmit 2 separate signals but using the same carrier. You can observe here M, L and MR, say left and right. So, what is that application? It is used for FM radio broadcasting. The requirement for FM stereo multiplexing is that it should be compatible with monophonic receivers. It is used to send 2 different elements of a program so as to give a spatial dimension to its perception by a listener at the receiving end. Say for example, if you have 2 sections in an orchestra, say one is the vocalist and another one is the accompanist, both are using the same channel at the same time. One is playing some instrument, one is singing, both should be mirrored across in a single slot. So, this is the case where FM stereo multiplexing comes into picture. The specification of standards for FM transmission is, first one is the transmission has to operate within the allocated FM broadcast channels. Within the available channels only it has to fit in. It has to be compatible with the monophonic radio receivers. These are the 2 important things you have to note. So, coming to the block diagram of FM stereo multiplexing, that is the multiplexer part. So let us denote ML of t and MR of t, which is like left hand and right hand of the microphones at the transmitting end of the system. They are applied to the matrixer, which generates the sum and difference. This is plus plus, so this generates the sum. This is plus minus, so this generates the difference, which generates sum and difference signal. Sum is ML of t plus MR of t. Difference is ML of t minus MR of t. So the sum signal, it is taken as it is, without any processing. It is given as it is. It is applicable or it is available for the monophonic reception as it is. The difference signal, now we have a 38 kilohertz subcarrier. Here whatever the frequency what we are using, it is 19 kilohertz. Generally the crystal oscillator, it generates a signal of 19 kilohertz. So we have a frequency doubler, so the frequency now is 38 kilohertz. Subcarrier, it is applied to the product modulator. So what is the output signal? It is a DSB-SC signal, double sideband suppressed carrier signal. And the multiplexed signal M of t, it also consists of a 19 kilohertz signal and a DSB-SC signal to provide as a reference for coherent detection of the different signal at the receiver side. So now the multiplexed signal M of t is given by ML of t plus MR of t. This is the sum signal and this is the difference signal, that is ML of t minus MR of t into cos of 4 pi FCT, that is 2 times doubled, 2 times of 2 pi FCT. So it is 38 kilohertz DSB-SC signal and you have a k times signal which is centered at Fc. So this is 19 kilohertz and this is 38 kilohertz signal. So this is what happens in the multiplexing type at the transmitter side. Next we will see the demultiplexing of the FM stereotyping. So whatever the message signal M of t is coming, it is applied to the demultiplexer. The individual components of the multiplex signal M of t, they has to be separated into 3 components using appropriate filters. The recovered pilot signal, it is frequency doubled to here to produce the desired 38 kilohertz carrier frequency. Frequency doubler is that, which enables the coherent detection of the DSB-SC modulated by, thereby recovering the signal ML of t minus MR of t. So the baseband low pass filter in the top of the figure, it is designed to pass the signal. This one is sum signal and this is the difference signal. So finally what happens is, the simple matrixer, it reconstructs the left hand signal ML of t and the right hand signal MR of t, and then it applies them to the respective speakers. So this is how the FM stereo receiver works. Basically we are doing the separation of the multiplexed signal at the receiver side. So let me just summarize what we have discussed in this video. We have discussed about demodulation of signal, FM signal, FM stereo multiplexing, FM stereo demultiplexing. So in the next video we will be discussing about the phase locked loop indirect method. You will see both linear model and non-linear model of the signal and what are the non-linear effects in the FM system. Thank you.